deployment scenarios and impacts at scale. And I'd like to introduce Daniel Posen. Daniel is an associate professor of civil and mineral engineering at the University of Toronto. Within the CanCO2Re initiative, he's coordinating the activity examining the environmental equivalence of CDR deployment scenarios. Thank you, Daniel.
Thank you. Okay, cool. It is not an intuitive remote. I need the mic because there's people online, is that right? Okay, cool. All right, hey everyone, thanks and welcome. This is actually, it's one of the highest activity numbers in the project because part of what we're trying to do is synthesize a lot of the other work that you see going on. So we've got a number of nice sessions today related to this idea that we're looking at all these different technologies and we're trying to understand how they interact, and our activity is trying to translate that into what this means at a larger scale, right? And so I've got a few intro slides here, but really then I'll try and get out of the way to let our presenters speak. But we've got this idea, right? We've got these global models or national models, whatever you take, where we see very, very wide range of CDR deployment needed to meet climate targets, either projected under different scenarios of carbon price or different levels of carbon removal needed to stay within climate targets. So this is an example out of actually CanCO2Re's paper, one of our speakers today, not the paper he'll be talking about, but to show, I mean, again, this massive range from the global integrated assessment models of how much deployment we're going to need to stay within climate targets. And within that, there we go. And so within that, right, there's this implied range of how much mitigation are we going to do compared to how much carbon removal we're going to do to either offset over emissions in the past or to deal with our residual emissions, right, to deal with the portions that we can't offset. And so we have this idea that these nominally equivalent scenarios can lead to very different outcomes. The idea that there's different pathways that theoretically should have the same greenhouse gas emission outcome that should lead to the same climate targets. But on the left here I'm showing, and these are stolen from other places, this is a figure I made when we were doing a paper on bioenergy, but the idea that there's all these other environmental impacts, right? So that when we think about, for example, this comparison between decarbonizing a hard-to-abate industry versus letting them continue to emit and using carbon removal to offset that, both of those can maybe result in the same greenhouse gas emissions, but there may be other co-benefits or co-impacts that we're worried about around things like resource use, around things like water use, air pollution, and various other things that would lead these two scenarios that are seemingly equivalent to not be. And that's on the left. On the right, we're going to hear from Kirsten Sickfeld today as well in one of our later talks around the fact that we can make the equations work. We can look at how much greenhouse gas emissions in terms of global warming potential we've emitted, and we can remove the same amount through carbon removal. But there's a big difference between carbon neutral versus climate neutral, right? And the idea being that a whole bunch of emissions, especially if it's a mix of greenhouse gases followed by a bunch of removals, especially again if it's only one species, may not lead to the same outcome overall for the climate. So we're going to think about that as well. And then we're going to think a little bit about the fact that these pathways, I showed all that wide range of scenarios for how much CDR we might need going forward. We're going to have a very nonlinear, messy way to get there between now and 2050, 2060, wherever we're going. How do we think about the future of our energy system? How do we think about the future of where and how we're deploying these different carbon removal scenarios and their implications? And how do we plan accordingly to make sure we're flexible around, not putting all our eggs in one basket, not sort of assuming that we're waiting for the magic technology to come online, that we don't know how the future is going to evolve. And there's lots of models out there that will do these projections for, again, the energy system and climate dynamics and these things. Human systems are notoriously unpredictable. We don't have any idea. If anyone tells you they know what the energy system looks like in 2050 or how we're going to get there, they are wrong. Every projection we've ever made is wrong. But how do we think about making these projections in a way that's still helpful and that will be robust to these uncertainties? Come on. Which way do I have to point it to make it work? There we go. Okay, so that's a little bit of the motivation of what's underlying what we're doing. As part of, again, what we call Activity 13 within the CanCO2Re project, we came up with this idea of looking at the environmental equivalence or the environmental non-equivalence of CDR deployment scenarios, right? So looking at this competition with different mitigation activities, understanding the overall climate impacts, not just the GWP carbon impacts of these scenarios, and then linking these things to a range of sort of a new generation of climate models or things that will allow us to test scenarios much more rapidly, much less expensive, less computationally expensive climate models. Think about linking in these different CDR scenarios with an energy system model to understand the interplay between, well, how much energy are we going to need if we're going to be rolling out a whole bunch of direct air capture, and what does that mean for all of our other efforts to decarbonize? Okay. So you're going to see a little bit of that as part of this project. So you're going to see, well, you're seeing me already, and you'll see at least a couple other faces on there, and then you'll see some other folks from related projects. So you've got your 5-minute introduction from me. You're going to hear from Ferris about identifying points of competition, potential competition between CDR and mitigation, which will then allow us to later on in the project think a little bit more about those co-benefits. We're going to see a little bit from Kazra on the role of uncertainty in determining the CDR projections, long-term energy planning from Juan Moreno-Cruz, and then finally, we've got a good chunk of time towards the end on the climate impact side of things with Kirsten Sigfeld to talk to us a little bit more about how we actually model these things and the carbon cycles and the actual Earth system dynamics. And then I've left some time at the end for discussion. Like I said, my role is to get out of the way though, and so with that, I would like to introduce Ferris Abdullah, who's a PhD student at the University of Toronto. You're already mic'd up? Wonderful. Forward, back.
Perfect. Thank you. Just making sure that everybody can hear me. Cool. Perfect. Okay. So thank you, Daniel, for that great introduction. As Daniel mentioned, my name is Ferris. I'm a PhD student at the University of Toronto, and today I'll be talking about identifying competition areas, specifically across economic sectors, where there's some dynamics at play between emissions mitigation and carbon dioxide removal, CDR. Oh, sorry. Okay, so today's climate policy landscape is shaped by the need to reach net zero emissions by mid-century, as per the Paris Agreement climate targets. This entails reducing emissions as much as possible, what we call mitigation, and then using CDR to offset whatever remains. Mitigation strategies include shifting to renewables, electrification, increased efficiency, while CDR refers to technologies that remove CO2 from the atmosphere, like DAC and BECCS. However, there's growing concern that the availability of CDR could reduce the urgency to cut greenhouse gases right now, a phenomenon that's known as mitigation deterrence. Essentially, actors might rely on future carbon removal instead of pursuing more ambitious mitigation right now. The Paris temperature targets require both deep emissions cuts and CDR deployment for residuals. But there's still uncertainty over how much CDR will be needed, how quickly it can scale, and where it might displace mitigation. This study focuses on sectoral competition between CDR and mitigation. We define competition as the tendency of sectoral emissions to rise when more CDR becomes available. Added CDR can allow some sectors to emit more, while the overall balance remains at net zero. So, competition reflects which sectors decarbonize the least when CDR expands. Okay, so overall, this research project explores areas where mitigation gets displaced when CDR capacity increases, and we began by collecting Canadian emission scenario data from 4 models, which we will go over in more detail in the next slide. We classified these net zero scenarios into high CDR and low CDR subsets. So basically a high CDR pathway to net zero and a low CDR pathway to net zero. We then examined this competition in 5 steps. First, we identified which sectors, sorry about that, missed a click there. First, we identified which sectors showed the strongest competition between mitigation and CDR by evaluating how their emissions levels changes with increased CDR. Second, we quantified that competition. How much do emissions rise per additional megaton of DAC deployed? Third, we explored how delaying DAC rollout affects near-term mitigation. Fourth, we compared CDR and emissions trends across our 4 models. And finally, we expanded globally, assessing how this competition plays out in 18 other countries using CD-Links data to capture broader patterns in CDR mitigation dynamics. So, to analyze these dynamics, we compiled scenario data from 4 major sources. So the first one is Navius's GTEC IESD model, which is an energy economy model with 324 scenarios. It includes 10 sectors and varies key assumptions like solar, wind, and battery costs, oil price, and DAC availability. The second one is CD-Links from IESA, a global integrated assessment model database. We extracted 524 Canadian scenarios and over 5,000 international ones. These span diverse policy frameworks, socioeconomic pathways, and various CDR technologies. Third is Canada Energy Regulator's Energy Future 2023 report, which includes 3 scenarios and tracks emissions annually by sector all the way through 2050. And finally, we have Trottier's Energy Outlook 2021 report, which focuses on net zero pathways through 2060, including scenarios around carbon pricing and biomass and BECCS availability. So these are optimization or equilibrium-based models that simulate how energy and economic systems evolve over time and under policy constraints. They solve for least cost pathways under constraints like a carbon budget or a long-term policy target like net zero or a carbon price. They forecast sectoral energy demands and emissions based on assumptions about costs, technology learning curves, and socioeconomic conditions. The model outputs that we make use of are emissions trajectories per sector and CDR deployment. These databases tracked emissions across a wide array of sectors, including variations of residential and commercial buildings, land use and/or agriculture, transportation, electricity and/or utilities, and industry. Navius tracked negative emissions primarily using DAC and some land use, while the rest looked at multiple modes of sequestration, including DAC, BECCS, land use, and even enhanced weathering in a couple of cases. Together, these data sets provide emissions and CDR values across multiple timelines and policy contexts, allowing us to assess which sectors rely more on CDR when under different technological and economic assumptions. So, our first step was to identify how sectoral emissions respond to added CDR deployment, i.e., which sectors decarbonize the least when CDR capacity expands. To do this, we grouped scenarios by extremes of CDR deployment. So you have high versus low, or on versus off in the case of Navius, and then compared sectoral emissions between those extremes under the condition that all scenarios, whether high or low, still reach net zero. In the Navius model, we were able to directly compare 108 net zero scenarios with no DAC to 108 scenarios with DAC. The figure on the left shows box plots of 2050 sectoral emission differentials. That is, the difference between high and low CDR pathways for those 108 scenario pairs. As we can see, the increase in DAC sequestration on the bottom right is offset by increases in sectoral emissions, with the 4 sectors with the highest emissions rebound being depicted here: industry, light transport, mid-heavy transport, and oil and gas. The industrial sector exhibits the highest emissions increases, accompanying increased DAC deployment, followed by, on average, mid-heavy transport and oil and gas. In other data sets, CDR levels were influenced by exogenous variables like policy targets. So we inferred high versus low based on model outputs. For example, based on the Trottier data, and as depicted in the subplot on the right here, we compared sectoral emission differentials between 2 policy roadmaps: net zero by 2050 and net zero by 2045, an accelerated case. In this case, the results indicate that the energy production and electricity sectors compete most for CDR, likely because of the more stringent requirements of an accelerated energy transition, and the paramount role, of course, of energy in economy-wide decarbonization. These differentials form the foundation for quantifying sectoral competition in this step right here. So after identifying where competition exists, we move to quantify it. Specifically, we asked, how much do emissions in each sector increase per unit of added CDR? Using the Navius scenarios, and for each sector and year from the 4 depicted, the 4 most impacted, we basically normalized the emissions differences by the DAC difference to get a marginal emissions rebound, measured in megatons of CO2 equivalents emitted per megaton of added DAC capacity. The 4 shaded regions here represent potential ranges of emissions rebound for each sector. So, in 2050, the industrial sector showed the strongest competition. Emissions increased by between 0.27 and 0.28 megatons of CO2 equivalents per megaton of added DAC. Medium and heavy transport followed at about 0.7 to 0.19, while oil and gas ranged between 0.1 and 0.2. Other sectors showed lower or negligible responses, Light transport peaked at 0.14, but remained mostly under 0.1 in everything up to around 2047 or so. These results helped quantify the degree to which certain sectors shift the net zero burden onto CDR when it becomes available. Okay. Next, we explored how the timing of a CDR rollout is associated with changes in sectoral emissions levels. So the question was, if DAC was deployed later, by how much more do sectors mitigate in the meantime? Okay, so again, using Navius, we sorted scenarios by the year DAC first appears, either 2035 or 2040. This figure presents the percentage drop in emissions due to a delayed DAC rollout for each sector with time. We can see that delaying DAC is associated with stronger near-term mitigation, which makes sense, since we have to meet net zero anyway at the same time. Light transport here showed the biggest drop, emitting around 41% less in 2050 in scenarios where DAC rolls out in 2040 instead of 2035. Sectors like light transport already have low carbon alternatives available, like EVs. And without DAC to fall back on, the model ramps up direct mitigation sooner. We also saw emissions reductions in oil and gas, medium and heavy transport, and industry. These sectors likely benefit from assumed CCS expansion or demand-side reductions. The takeaway is that as DAC is delayed, mitigation does accelerate, especially in the sectors with feasible alternatives. Okay. To test the consistency of our findings, we conducted an intermodal comparison across all 4 Canadian data sources, so Navius, CD-Link, CER, and Trottier. Each model uses different assumptions, time horizons, and policy inputs. So we first had to standardize emissions profiles across the models and harmonize sector definitions and convert all emissions to units of CO2 equivalents so that when we actually do end up comparing them, we'll be comparing apples to apples. This figure presents absolute sectoral emissions and DAC sequestration in 5-year intervals from 2030 to 2050. The results show large variability in both emissions and CDR deployment. Navius tends to assume higher DAC availability. You can see that in the very first slab, starting around 2040, while CD-Link, CER, and Trottier rely more on land use or BECCS. Multiple models exhibit negative sectoral emissions in some cases due to the adoption of sector-specific CCS. Despite these differences, most models agree that emissions do decline over time, and that sectors like transportation and oil and gas consistently shrink. However, we also observed outliers like industry emissions increasing in some scenarios despite rising CDR, as you can see in the case of CD-Links in the middle slab. These differences reflect uncertainty in cost, technology, and policy assumptions, highlighting the impact of modeler judgment in these IAMs. And finally, we extended our analysis to include 18 other regions using CD-Links data. These include the US, EU, China, India, Brazil, Japan, and a few others. These countries were selected because they were the most data-rich and contained the highest number of model scenario combinations to allow more robust analysis. The figure on the left presents total sequestration by CDR mode via DAC, BECCS, and land use. The figure on the right tallies which sector competes most for CDR in each of the 19 regions we studied, and both account for only our universe of 19 regions. So BECCS dominates as the primary CDR method, making up about 2/3 of projected removals by the century's end. DAC grows steadily but remains second, while land use methods grow more slowly due to constraints like biodiversity and food security. In terms of competition, the building sector, including both residential and commercial buildings, ranked first in 8 of the 19 countries, meaning it reduced emissions the least as CDR expanded. It was followed by transportation in 6 of the countries, agriculture in 4, and industry in 1. This variation reflects national differences in infrastructure, economic structure, and technological readiness, and confirms that CDR mitigation dynamics are context dependent. Okay, so to summarize some of the key takeaways, first, sectors facing moderate to high decarbonization costs or technological barriers to decarbonization tend to rely more on CDR when it's available. This is true for both Canada and across the globe. Second, delaying DAC rollout is associated with stronger near-term mitigation. We saw this mostly in oil and gas, light transport, and medium and heavy transport. all of which emitted less when DAC was postponed. Third, competition between mitigation and CDR is regionally variable. In Canada, it's industry and transport. But globally, buildings and transport lead in emissions rebound as CDR deployment increases. Fourth, even with the same net zero goal, modeler judgment and differing assumptions about technology costs, policy levers, and timelines drive different sectoral outcomes, which makes improving model transparency a key outcome that is, well, I guess, very desirable for climate policy making and for target setting. Identifying these sector-specific trade-offs can help guide policy and ensure that CDR complements rather than replaces mitigation where decarbonization is still feasible. Okay, so building on these findings, our next steps focus on deepening the analysis in two main areas. First, we'll assess the environmental implications of high CDR versus high mitigation pathways. That means examining how different strategies affect land use, energy and water demand, material inputs and intensity, and air quality, especially in select high competition sectors that we just identified, like medium and heavy transport. Second, we plan to assess the design and performance of resilient CDR portfolios. By modeling performance under a range of uncertainties, like fluctuating sequestration costs, technology learning rates and curves, land constraints, and tech adoption rates, we can identify strategies that hold up the most under conditions of deep uncertainty. Ultimately, the goal of this and future research is to inform policy making that ensures that carbon removal doesn't crowd out mitigation in sectors that can and should decarbonize. Balancing removal with reduction will be essential to crafting effective, just, and durable net zero strategies. And thank you. That's all I have.
Don't go too far. And so I didn't announce this at the beginning, a little different than the other sessions. I'm going to suggest that if there are any clarifying questions or anything directly related to each presentation, we'll take like one or two after each talk, and then we'll leave time at the end for the panels. And I saw a few hands shoot up right away. I think Jordan may have been first. How do we do? Do I give you my mic? What do I do? No, come to the mic. There's people online. You have to walk if you want to ask
because
a question.
my question's really short. You kept saying delayed DAC and DAC coming on at a certain time. I'm wondering what that actually means. Was it a certain amount of DAC? Like right now we have pilot projects going on. I'm assuming that's not DAC online. So what's the actual key definition of that?
So when I say that, basically I mean that sequestration starts at, I set a buffer that's like above, I believe it was around 1 megaton or something, something like that. I can get the exact number for you, but basically, as soon as that buffer is crossed, that means DAC started that year. And we found basically 2 years that were in those different settings that actually made it out, which were 2035 and 2040.
And like a lot of these are model constraints, right? Where they're not trying to capture every individual pilot project. It's more like in the model, when does it start to take off? This will be the last question for this talk.
First, I get really interesting. I guess first question, 2035 was the earliest that it can come on?
Earliest, but like above that buffer, yeah.
Interesting. Oh gosh, yeah. I guess that's only 10 years away. But,
yeah.
And then, so it's kind of interesting to see how it interferes with just traditional abatement, but did you look at the overall emissions reductions? So you said, you know, putting DAC online 2035 has this much effect on, you know, reducing reductions. So people, you know, preventing reductions, I guess.
Well,
but how does that affect the total emissions? So if DAC is online 5 years earlier, and then that means industries abate later, is that still beneficial, just slightly less so, or is it actually harmful if it's on earlier? If that makes sense.
Well, let me put it this way. In 2050, everything's going to be at 0, regardless whether you start in 2035 or 2040. Yeah. In 2040, that's the model assumption, yeah. In 2040, if DAC rolls out significantly in 2040, you're going to notice something like 40%, 40% increased drive towards deep decarbonization and light transport, for example. So if the case starts in 2035, emissions would be 40% higher. So I'm not sure.
Accounting for the difference in DAC as well? Like, I guess my question is.
Well, DAC would be.
Okay. 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 But even at the 2035, like at 2040, if you haven't, or let's say in 2039, if DAC is online versus not online, is the total emissions significantly different?
The difference is the models were generally run under emission constraint that's binding, so it doesn't show.
Oh, and the step down is consistent? Okay, okay, thanks.
All right.
Thank you.
We're probably going to end up having a shorter discussion, but I still think it's good to have questions right away. All right, so our next speaker is, oh no, Kazra, I didn't ask how to say your last name, panel at the end. But in the meantime, thanks, you're already here. So we have Kristen Sickfeld, and I don't know your exact title, is a distinguished professor of climate science at Simon Fraser University. Within the CanCO2Re project, she is coordinating the activity examining the environmental equivalence of CDR deployment scenarios, along with me.
Okay.
Kristen, take
Yeah.
it away.
Okay, thanks for the introduction.
So
and I need,
forward, back.
Okay, and I need my talk. Okay,
There you go.
Okay, good. All right. Good. So thanks for the full introduction, and yeah, good afternoon, everyone. So we've talked a lot of CDR, and ultimately the reason we're doing this is because we want to reduce the concentration of carbon dioxide in the atmosphere, and we want to mitigate warming. And so what I'm going to do here is talk a little bit how removing carbon dioxide from the atmosphere affects the actual carbon cycle and also affects temperature. So I'm not going to talk about other climate science metrics to make it easier. So generally, I'll talk about the effects on the carbon cycle, on temperature. We'll see that there are not only the effect of the carbon dioxide that we're removing, but also from other effects. So Daniel mentioned that earlier in the introduction, because there are co-emissions both in the fossil fuel burning space, but also in the CDR space. And for these reasons, when we talk about carbon neutrality, we may not necessarily achieve climate neutrality. So I'm going to unpack that a little bit, and also the implications for net zero scenarios. Okay, so let's talk about the carbon cycle a little bit. So when we emit a ton of carbon dioxide into the atmosphere, only about, so this is indicated by, so G here means that the geologic reservoir, so we're taking carbon out of the geologic reservoir, we're putting that into the atmosphere. And when we do this, then that carbon repartitions into the land and into the ocean, which are those carbon sinks, right? So that only about half of that carbon actually remains in the atmosphere. So the ocean and the land do us a huge service because they actually mop up half of the emissions that we put into the atmosphere. So now what if we remove a ton of carbon dioxide? So this is shown at the bottom. So now what we do is either we remove carbon dioxide directly from the atmosphere via DAC, or through land-based methods as in BECCS. And so now what's happening is essentially the same redistribution mechanism, but in reverse, right? So now we're removing carbon dioxide from the atmosphere. So now what the land and the ocean do is they return some of that carbon into the atmosphere. So what this means is that if we remove sort of net, if we remove 1 ton, only about half of that will remain out of the atmosphere. So when we're talking, so Kazra gave sort of introduced this sort of nicely because he defined these two roles for CDR. So when we think about CDR as an offset to emissions, and we're still in a state of the systems where emissions are net positive, so we're emitting more than we're removing, then we go with the upper picture. So we're still sort of, so land and ocean will take up carbon dioxide. But let's say once we go into the space where there is a net negative emission, so we're removing more than we're actually putting into the atmosphere, then we'll see on a global level those sink returning carbon dioxide back into the atmosphere. And so we can quantify this by running global climate models. So these are experiments with these very complex Earth system models. So there's a whole bunch of them. So this is a figure from the IPCC report. So the experiments that we did with these models is we instantaneously removed 100 gigatons of carbon. That's a huge amount. in Earth system models, we need a very large signal because we have interannual variability, right? Sort of, so as we know, weather varies from year to year. So we need a signal that is actually larger than that interannual variability. And so we need at least 100 gigatons in order to be able to detect a signal. And so here the experiment, so this is net removal from the atmosphere, but I want to emphasize that this is also true, let's say in a situation where we have a business as usual trajectory, and from that we do remove carbon, and then we look at the difference between our business as usual plus CDR relative to the business as usual trajectory. So here the experiments are set up at net removal, but this would also be true and if we're comparing the effect of CDR versus a trajectory that does not include CDR. And so what we see is at the top, what you see is that when you remove that carbon instantaneously, your CO2 in the your concentration of carbon dioxide in the atmosphere declines very rapidly, but then it comes back. So this is the so-called rebound effect. And in the middle and at the bottom, you see that that carbon that is now re-added to the atmosphere comes out of the land and the ocean. And so then you can ask, well, how much is then replaced? And so here these models show that there's a little bit of uncertainty if you do the math. So in the upper model, you see that the concentration almost rebounds to its initial value. So there the effect is 15%, whereas in other models it's around 35 to 40%. Okay, so so then we can calculate a removal efficiency, and we can ask, or effectiveness, and we can ask of the CO2 that we actually remove out of the atmosphere, how much remains out, right? And that is our removal effectiveness. And then we can ask, well, does this depend on how much we remove? Does it remove from what state? Does it depend on what state we remove it from? And so again, with simulations with Earth system model, we find that first of all, this removal effectiveness depends a little bit on how much we remove, not so much, but it depends quite strongly on the state from which we remove it. And I would say sort of one interesting result is that actually this effectiveness, so the amount of carbon that stays out of the atmosphere after we remove it does decrease with decreasing initial atmospheric CO2 concentration. So which means that if we do this when CO2 concentrations have already come down, it's actually harder to do than when CO2 concentrations are higher, which especially when we think about net zero pathways is sort of not so good news. Okay, good. So this is carbon dioxide, sort of concentration of carbon dioxide in the atmosphere. But ultimately, what we're interested in is temperature. So we want to know when we remove carbon, how much cooling do we actually get? And again, Kazra's presentation earlier introduced us to this idea that there's this proportional relationship between warming and cumulative carbon emissions into the atmosphere, and that same relationship holds more or less also for cooling. So, so we can say that the amount of cooling that we get per unit of carbon removed from the atmosphere is roughly proportional to the amount of carbon removal. Okay, so that gives us a nice metric, because then we can, once we know the amount of carbon that we remove from the atmosphere, if we know sort of the slope of that relationship, which we call the transient climate response to removals, then we can calculate what the temperature benefit is from that. So this is as far as carbon goes, but as I hinted at earlier, we also need to think about the other effects in which both emissions into the atmosphere or removals out of the atmosphere affect climate. So first of all, both emissions, but also some CDR methods go along with emissions of other greenhouse gases into the atmosphere. So for example, if we think about bioenergy plantation, we may fertilize some of them, which then results in emissions of nitrous oxide into the atmosphere. Or when we think about peatland restoration, that comes with additional methane emissions. CDR methods also emit aerosols. So aerosols are particulates. They're not gases. So for example, when we plant tree, they may emit volatile organic compounds or VOCs, which then interact with clouds and so on and have an effect on climate. And then with approaches that modify the surface of the earth. So again, this could be planting trees, but it could also be BECCS if bioenergy replaces some other type of land use, or even very large scale DACs if the footprint is very large. That influences the fluxes of energy at the Earth's surface. So things like the reflectivity or the albedo, the evapotranspiration, so the extent to which plants can access water and transpire that into the atmosphere. And so this here is a figure from the IPCC report, which summarizes some of these non-carbon dioxide effects here within this blue box. Here, so this is a complex figure with a lot of details. What you find in the vertical, these are the different CDR methods. They're ordered by the time scale of carbon storage. So we have the biological ones on top, where the time scale is decades to centuries, to the more geologic approaches at the bottom. And then what I want you to look at is those squares within the blue frame. And what you see, there's a number of biogeochemical effects. So these are the non-CO2 greenhouse gas emissions and aerosol emissions, but also these biophysical effects, which refer to these changes in the surface energy balance. And for example, if you look at let's say at BECCS, which is the second last from the bottom. So you see some of these purple boxes, which is an indication that there are additional effects, but also potentially some effects on the surface energy balance. Okay. We think that balancing an additional ton of carbon emitted into the atmosphere with a ton of removal is the same thing as not emitting that ton of carbon, right? So that's kind of this idea behind the carbon neutrality, that instead of not emitting, we balance the emission with the removal, and then we end up in the same state. But again, this is only in a very idealized way, because again, the emission system, so when we when we cut down forests, or when we burn coal or natural gas, we emit carbon dioxide into the atmosphere, but also a suite of co-emissions, so non-CO2 greenhouse gases, but also aerosols, right? But then on the other hand, the solutions to then sequester that carbon from the atmosphere and then store it in different reservoirs have their own non-CO2 greenhouse gas co-emissions and also effects on the surface energy balance. So that perhaps maybe if in theory we achieve, we can balance a certain amount of emissions with a certain amount of removals, because of these non-equivalencies between emissions of removals, we may balance the emission, but not necessarily the climate impact. Okay, so this is why when we think about the climate effects, we need to think beyond carbon. So to demonstrate this, we did an experiment, again with an Earth system model. So this is from from a PhD student in my group. So here we chose reforestation. So the extent is shown on the left-hand map. So what we did is we reversed historical deforestation. So essentially, we restored the state of forests from pre-industrial times. And you see by these green areas where additional forest grows. And what we did is we calculated how much carbon dioxide do these forests sequester. And so this is shown in the middle. So that's the amount of CO2 that these forests sequester per year over about a century. And then in our model experiment, what we did is we quantified an additional amount of fossil fuel emissions, which is exactly the same as the amount that is removed by reforestation. So in a way, this would be sort of a net zero state, right? So that we emit additional carbon into the atmosphere. We balance that by forestation-based removal. And so let's say through our conventional understanding, we would think, okay, good, so this is net zero. So in a way, this is climate neutral. And what we find that it's actually not. So we find that maybe I should go back to show what the reference case is, right? Sort of then what we do is we compare the result of this net zero scenario where we compensate emissions with removals with the baseline, so that's the red line here on the right-hand side, which is a true zero baseline. Okay, so this is an idealized scenario where we actually, instead of going to net zero, we go to real zero. We go to zero emissions, and then we ask, is the climate outcome actually the same? And here, by comparing the green and the red, you see that that's actually not the case. So we get a higher atmospheric carbon dioxide concentration. So just in a nutshell, this is because planting trees warms the surface air in some regions, which then affects fluxes at the surface, resulting in emissions of carbon from the land. And then in addition to that, so this is on the right-hand side, this higher atmospheric CO2 concentration is then also amplified by what are called these biogeophysical effects, which are the effects on the surface energy balance. So forests are darker than grasslands or crop regions. Also, the roots are shallower, so they're not able to access water in the soil as deeply. And so all of these effects affect temperature as well. And I would say, so this is a sort of quite a significant effect. We see that by the end of the century, we end up with 0.1 and even a little bit more warming than if we did not emit those additional emissions and offset them with reforestation-based removals. So this is one model. So this is, so sort of next step would be how robust is it? All of these effects are highly uncertain. If you repeat that with the different Earth system model, you most certainly get out different numbers, but qualitatively, this result is quite robust. That if you compare net zero scenario with the true zero scenario from an Earth system perspective, you cannot expect them to be equivalent. So then, very quick summary. So only a fraction of the CO2 that we remove by CDR remains out of the atmosphere. So this, as long as we're in this phase where we offset emissions with removals and we're in a net positive emission state, this doesn't matter, but it becomes important when we transition to net negative emissions. Then the amount of carbon dioxide that remains out of the atmosphere, which I introduced as this measure of effectiveness, is slightly sensitive to how much we remove, but is more strongly sensitive to the state from which we remove the carbon. The net effect of removal on surface air temperature is not only determined by the CO2 that we remove, but also by these non-CO2 effects. And this is why we need to consider these Earth system effects in net zero scenarios that balance additional emissions with CDR. So I leave it here, and I'm happy to answer any questions or move to the discussion. Thank you.
Well, I will say you stuck to your time, so we can take maybe 1 or 2 questions for Kirsten, then we'll have about 5 minutes left for the panel, which I know isn't very long, but we're going into a break afterwards anyway. So we'll start with any questions for Kirsten? No.
Yeah, sure.
He wants you to go back a slide.
I'll just go back to slide. Okay, didn't hear that. Yeah. Okay.
Oh, not a question, just a picture. Okay, excellent. Well, let me invite the others to come on up while we're getting the first question for Kirsten. Yeah, Marashkan. You need the microphone, people online.
Thanks for the presentation. I have a question about the third bullet point here. So regarding all the research that is underway and our evolving understanding about the distinction between climate zero and net zero, do you think that we are going towards the direction that policymakers or other practitioners in their toolbox, when they're trying to have a more sustainable future, they have these tools that you can give it a given or at least a range of surface temperature or CDR, and they can tell you what is the optimal path in terms of CDR deployment?
Well, I think the way I don't think about as much in this optimization frame. I think I would think about it more in an equivalency frame, right? Right now, I think our factor is 1. So we say, okay, there's one amount of 1 ton of CDR is equivalent to 1 ton of emissions. And I think what it means to introduce these other factors is ideally, if we can, to come up with some sort of scaling factors. So for example, that allow you to say, okay, good, if I plant a forest here outside of Calgary, then this is going to be the temperature effect, and therefore I need to discount my CDR effect by that much. Whether that's possible is that I would say is a complicated question that the science is trying to answer. But I think, ideally, if we can come up with these factors, that would make the problem tractable.
So Kirsten, you're welcome to stand or you're welcome to take a seat. Well, so the question can be for anyone, including Kirsten. We go on to the rest. I don't know who is first. I guess, Sean, the mic's on its way to you.
So I have a question. Maybe this is equally for what's coming next in the discussion. But so Kirsten, you said something which I think I think I've known, and I think many other people know, but that a removal and a reduction are perfectly the same thing until we reach net zero, right? So I think that tells me that a reduction and a removal should cost the same thing because they do the same thing. It's one price, right? Yet we seem to be in a community where somehow removals are looked at as more valuable or different in some magic way than a reduction, right? And we have people who are willing to pay very, very large sums of money for reductions, but they're not willing to pay the same amounts for removals, excuse me, but not for the same amount for reductions. So I'm just curious if, it sounds very counterintuitive to what science tells us.
I think what is happening in that case is that obviously there is a political reason, but I'm trying to abstract from that. There's a technological reason that is actually useful. And it's actually, from that perspective, you don't have to alter the production function as a firm. There is another industry that can deal with it. And it's not the first time we do this, we do disposal always offsite, somebody else always manage disposal for us. So I think that is why people are willing to pay for it. It's mostly because there is a cost response at the individual level, and these are all analyses that are at the global level, but at the firm level, they're costly. And that's why government matters, because government should be the one actually saying, no, you have to do it because it's the cheaper thing. Since that, then people are going to pick what is cheaper for them, not necessarily for society, and it ends up being something like DAC or something like that.
I don't know if I'm supposed to be on the panel or just muttering, but I'll add to that I think there's also a valid reason in terms of supporting a nascent industry, right? And thinking about the spillover and the long-term effects. On the flip side, of course, there are these, trade-offs in terms of, reductions usually come with co-benefits, right? You burn less stuff, you have less pollutants on other things. So whether it makes sense or not, I could make a case for it, but yeah. Did anyone else, or I think Maziar, you had your hand up. Yeah.
Hi, thank you for the presentation. It was very insightful. I just have one question. You mentioned that you're balancing the CDR and doing that with modeling reforestation. And you also mentioned something about it being a darker color, and I imagine that has to do with how much energy from sunlight we're absorbing. And my question is, well, in that case, shouldn't we just look at reforestation CDR and say that this is less effective than we think it is because it is absorbing more sunlight from the sun? And in fact, if we do like DAC, then that's 1-on-1, but if we do reforestation, that's like 0.95 for 1. Like, is that a more correct statement, or am I
Yeah, no,
missing the
I
point?
mean, absolutely. So I think that's what it comes down to. And I think with regard to reforestation, I would say it is vastly overrated in terms of the temperature effects it can achieve, especially here in Canada, in regions where we have snow cover. Actually, you get a net warming from planting trees. From a pure climate perspective, there are many other benefits to planting trees, so let's not get that wrong. But I would say yes. I mean, this is what it comes down to. That if we understand all these non-CO2 effects, then sort of perhaps we can classify CDR methods by the amount of cooling that we achieve by removing a certain amount of carbon with a given CDR method. Yes, but I would say from what we know, so we haven't, I think there are less studies that explore the land footprint of DAC, which sort of seems to be larger than perhaps was previously assumed. It was because of the land footprint of reforestation and the effect on albedo. What you say is certainly the case. Yes.
Thank you.
Question over here. I'm watching like this might be our last one.
Yeah.
Thanks everyone for the great presentations. And my head's spinning right now, and I don't even know what to think or do. So thank you for taking my sleep away from it. So Kristen spoke to us about the effect on GHG reductions on climate. And then earlier we heard about the models and what the models say on which technologies have the greatest impact on reducing CDR. And one of those is BECCS. On the other side, BECCS might actually increase, like, depending how you do it. So my question is, if we want to avoid a degree of warming the planet over than 1.5 degrees C in the next years, do we have to optimize all the CDR technologies right now in order to avoid that climate impact and also reducing the GHG emissions that we need to reduce? How do we solve this?
You're up, man.
Could you say the last part? Your question was, do we have to optimize all of the technologies as soon as possible?
Because, yeah, depending on the technology that you're using, it might have a consequence on the climate. So one thing is reducing GHG emissions. Another thing is having a target on the climate impact. Like Kirsten's presentation, it just blew my mind. So if we want to reduce GHG emissions and don't want to overshoot the climate impact, which is having a temperature, a gradient in temperature higher than 1.5 degrees C, then how do we solve it? Do we need then to optimize the technologies that encompass CDR in order to achieve this goal?
I'll give an initial quick answer, which is, so remember that these models are big, high-level, global scenarios with very aggregate projections. So like when the model's picking lots of BECCS, it's doing it because the modeler put in that BECCS is cheaper, right? And in some ways, it's spitting out part of what you put in. So I think the answer is no model's going to tell you the exact optimal mix you should be using. It'll give you insights into sort of generally, here's one that looks like it has promise, here's one that doesn't. I mean, I think certainly out of the climate modeling, right, if we find that, so seriously, forests have warming kind of long-term, or it's like a temporary effect?
It's as long as the forest stands.
Okay, so like that sounds, again, lots of other reasons, but that sounds to me like we certainly shouldn't be doing things that aren't achieving the goals. Beyond, I don't think this, so to Juan's talk, this is not a system we can optimize. I think it's a system we can design better or worse. Juan, I don't know if you have any thoughts on that. The idea of like, can it be optimized? But
So a couple of points. The first one, we actually produced a paper that came out earlier talking about this notion of the albedo and biomass. And there are so many other system forces in when you plant trees that are not captured by like high-level models necessarily. For example, effects on permafrost and things like this. And because of all those effects, it's very difficult to actually think of the net benefits or, because there's just too much moving at the same time. And then when we see these models, we actually think that the complexity of the system is the complexity of the model, but clearly that's not the case. The complexity of the model has been intentionally reduced. But again, I like speaking weirdly to my talk too, it's not that we cannot use those optimization results, it's that they fit into a larger setup that allows us to think better about the problem, but they're not solutions by themselves. And can I say one final thing? Oh no, you go, Kaz.
I just wanted to say that I don't have any opinion about optimization, but what I would say is that you should minimize the role, the first role of CDR, which was for the purpose of residual emissions, to preserve that for that critical need that you might have for the overshoot phase, because the CDR is not unlimited. You have a limited amount of potential CDR for different methods. So for the first one, you can maybe manage that with decarbonization. So try to have that minimum.
So I don't want to take too much of your break. This feels like a really good conversation. We're going to want to continue during the break, however. So please join me again in thanking our panel.
And thank you to Daniel as well. Thank you for moderating that. Thank you. So before you jump to break, and we are at break now, just a quick pulse check in the room. So we're asking, what is one idea that has stuck with you from the symposium so far? If you're having an existential crisis like Erica, maybe think of the second thing that pops to mind to combat some recency bias. But we're just doing a quick pulse check. Enter the slide, one sticky fact or sticky idea that's in your mind right now. Thank you.